In a previous video, I discussed how digital technology lowers transaction costs, even in the electricity industry, shifting organizational structure from vertical integration between generation, transmission, distribution, and retail into markets and contracts. And the example we saw from the 1990s in the US was the evolution from the vertically integrated firm into competitive wholesale power markets, with the unbundling of the generation portion of the supply chain into independent generating companies contracting with the buyers in wholesale markets, which are the retail load-serving entities, retail service-providing utilities in those wholesale power markets. The digital technological changes that we've seen of the past 20 years that are starting to affect the electricity industry through what's called smart grid technologies within the distribution network and around the distribution edge with customer-facing digital technologies like digital meters, two-way programmable communicating thermostats, and of course telephone apps that we can use to control and manage our energy choices are all changing, and this is a second wave of regulatory and institutional change that can be arising out of a technological change. And so right now in electricity, one big question is, what are the organizational implications of these digital technological changes? Will we see changes in the utility business model? And if we do, what form will that take? And there's been some recent very applied research. And for example, I was involved in doing a field experiment in what's called transactive energy. And this was in the Olympic Peninsula of Washington State in the northwest of the United States in the mid-2000s. And this was a field experiment where we had a set of households, and all of the households had two-way programmable communicating digital thermostats. And they could observe their consumption through a website in real time. And so we had a control group that had only the technology, but then we also had to get at the research question of how do people respond to the prices that they pay for electricity. We had 3 contract treatment groups. One had just a fixed price contract, very similar to the traditional utility contract. The second one had a peak and off-peak, high price, low price contract during very fixed and specified hours when the price would be high, and they could program that time into their thermostat. Although that's very similar, we can do that with existing digital technology that doesn't require the two-way digital communication and automation capabilities of the thermostat. The third group, though, very much does, and that was a real-time contract. And in the real-time contract, we structured the retail market as a double auction. And in a double auction, sellers submit offers and buyers submit bids. In this case, so the sellers would submit their offers, the buyers submitting bids were the thermostats that the homeowners had programmed with their preferences. And when different homeowners have different preferences, they have different willingnesses to pay. And so the logic of this is that if the price goes above a certain price, then the thermostat can automatically change the setting in the home to reduce the electricity use. And this is done through a standard double auction where you have the sellers submit offers to construct a supply curve, the buyers submit bids to construct a demand curve, and in any period you have a market clearing price. If the homeowner is not willing to pay the market clearing price in that period, they've programmed their thermostat to change their settings autonomously without any human intervention. And this is the idea of transactive energy, to use digital technology to change your settings autonomously without any human intervention. As you can see on the graph here, which is a schematic from one of the market periods of this field experiment, the programmable thermostats and the responses that homeowners programmed into their thermostats give you some elasticity on the demand curve. And this is a very important piece of research. It was the first transactive energy program and project, and it is a really good example of using prices to coordinate and balance supply and demand and to increase capacity utilization in the distribution grid. Because the responses to high prices, by reducing your consumption in those periods, if you shift your consumption to lower demand periods, you have a flatter, what's called a flatter load duration curve over time, and you have a more consistent use of capacity, and you can accommodate more demand with your existing capacity by having higher capacity utilization. And so this has been a very important potential change due to digital technology, the ability to automate consumer, even residential customer responses to price signals, and not just have it be big industrial customers or offices and commercial customers who respond, but even homeowners, because they can automate their responses using digital technology through their thermostats, through digital meters, through apps on their phones. There's another complementary technological change also going on right now, which is a change in distributed energy resources, or DERs. These distributed energy resources are things like solar photovoltaic panels on the roof of a home, or electric vehicles with battery storage, or even other independent, standalone, small-scale battery storage. The costs of producing solar PV panels and the costs of producing batteries have been falling very quickly in the past 5 years. These technological changes are again reducing the economies of scale in this industry, very much like the reduction of economies of scale that we saw in the 1990s with the combined cycle gas turbine. So the innovation in DERs is reducing economies of scale and changing the cost structure of the industry, making that cost structure more heterogeneous and diverse, which can lead to, again, another set of dimensions on which existing regulatory institutions and these new technologies don't fit well with each other. And so one potential institutional change that we could see is more retail competition and retail choice. Transaction cost reductions make competitive retail markets even more feasible than they are already. And this implies a second dimension for the unbundling of the vertically integrated utility. In the first unbundling in the 1990s, we saw generation becoming independent and generators competing in wholesale power markets. In this second round, we could see retail becoming even more competitive, with independent retailers competing with each other, and the utility retaining the ownership of the transmission and distribution wires. And so that is a potential implication for the utility business model of these digital and DER innovations that we are seeing in the early 21st century. These changes have some very important implications for something that is important in network industries, which is grid architecture. In the traditional electric utility architecture, you have large generators selling to end users, and the flow of current is one way from generators to end users. And the physical distribution and transmission, the wires networks, are constructed for that particular flow. With these digital and DER innovations and the changes in scale and the diversity now of the types of resources, solar on people's roofs, electric vehicles in their garages, microgrids, wind farms, all of the potential distributed generation, in addition to the still existing large-scale generation, the network architecture is going to change considerably. And one area of possible investment for utilities is in enabling the two-way flow along what used to be a one-way road for electrons. These innovations and changes in grid architecture do have implications for the utility business model. The implication of the fall in transactions costs and the bundling of the vertically integrated supply chain is that the utility will become a wires company. And in particular, one of the types of business models that is currently being discussed in many places in the US and Europe is the idea of a wires platform, that the utility can operate as a grid services platform, connecting parties for mutual benefit, and which we learned from platform economics, that a platform is an entity that provides benefit to two parties looking to connect for mutual benefit, and the platform provider connects them. And in particular, lately uses digital technology to connect them. For example, Airbnb or ride sharing. And so the idea of the utility being a grid services platform is one potential implication for the utility business model out of these innovations. One challenge to making this happen in the US is, of course, that regulatory institutions change much more slowly. And that change in regulatory institutions has to accompany changes in the utility business model in ways that are going to unfold over the next decade.